All right. So this week I wanted to talk about some different considerations when you're taking data, and this is what's known as sampling. So I think last time we talked about dealing with digitization and what happens if we don't have enough bits to store data. So this week we're going to talk about the other end of it, which is how fast we take data, and just like I say, some other considerations. So like I said last week, we talked about resolution in terms of the amplitude and basically the smallest Y step we can take. And that had to do with the number of bits you had available. And so we did a couple examples there with temperature, and if you only have 4 bits, how big does each temperature step have to be? Can you measure 1 degree, or can you measure a half a degree, or are you stuck with something like 10 degrees? This week we're also going to talk about time resolution, which is how big steps are in the x direction. So what I mean by that is, let's see here, can I draw on here? Screen, pointer options, okay. So like I said last week, we talked about, if you have some data, what are the biggest steps in the Y direction? This has to do with the number of bits. It's not bits, but it has to do with the number of bits. This week we want to talk about how quickly we take data, and it has to do with our sampling rate, which is which has to do with time. So there's a couple things with that. We have to worry about how fast we take data, how fast our system can take data. We have to worry about how quickly the sensors can change state. We have to worry about what's called the slew rate of amplifiers, and I'll talk about that more in a couple of weeks. We also have to talk about, do we have capacitors and inductors somewhere that are charging and discharging? And so what I mean by all that is, if you look at this, if this is what we want our response to look like, this nice square wave, the reality is things have to happen, so it takes a little bit of time. And then when we switch off here, it takes a little bit of time. So we just have to be aware that this is happening. And so talking in terms of sampling rate, we talk about this in terms of hertz. How many times per second can you collect data? And so and this is one of these things that you're going to have to figure out as an engineer, because if you ask your boss, how quickly should we take data for this, they're going to say, as fast as possible. And there's hardware to do all sorts of things. But what you have to do is you have to pick a reasonable sampling rate. If you sample too fast, you just end up generating, like I say, larger files and a lot of useless data. And of course, the more you sample, the more hardware you're going to need, and the more expensive hardware you're going to need. But then if you sample too slow, you run into this thing called aliasing, which I'll talk about in a minute, and you miss short-lived events. So what I mean by this is, suppose you're monitoring the moisture content of soil, and I don't know why you're doing this, but maybe you're doing this. You know that that's not going to change very fast. It's going to heat up in the day, and some of the water is going to evaporate out, and that isn't going to change very fast. If you sampled every 10 minutes, and took a data point every 10 minutes, that would probably be plenty to express how the moisture changes in the soil. You would not want to sample at 1 megahertz, taking 1 million samples a second, because it would just be a bunch of extra data that you have to go through. And like I say, more expensive hardware and all that. On the other end of the spectrum, if you were trying to, one of the ways you determine how fast the shock wave leaves an explosive is if you put your energetic material here, you place pressure sensors out this way, and so this gets set off, and you basically measure the pressure spike at each of these points. And the amplitude isn't so important so much as if you know this distance and you can measure the time that the spike arrives at each of these locations, velocity is distance over time. So why am I saying all this? Well, in order to capture that shock wave, which may be moving, something like a C4 could be moving 20,000 feet per second, you've got to sample really quick to make sure you got it. Your give me a pressure measurement, give me a pressure measurement, give me a pressure measurement. And you may need to do that 1,000,000 times a second. You may need to do that 1 megahertz or 10 megahertz or something like that. If you only sampled once a second, you would never catch it. So there are times where we have to sample really fast, and then there's other times we can get away with sampling a lot slower. Things like if you use a thermocouple for taking a temperature measurement. We'll talk about thermocouples in a couple weeks, but know that there's a wire, actually 2 wires, they're connected at a point, and we know that this point has to heat up. Now, if you put that inside of a housing, the housing has to heat up before the thermocouple can heat up. So we know that there's going to be a time delay there. So maybe we can only sample, I typically don't sample thermocouples much faster than 4 hertz because there's just no way the temperature changes faster than that. So you just have to be realistic about how quickly things are going to change and pick an appropriate sampling rate based on that. So let's talk about aliasing. And the deal with aliasing, I've got all these different signals here, and what's happening is this here is the true signal. This is what it would look like if you lived in a perfect world. And this is just a 10 hertz signal. It applies no matter what you're doing. So if you have some temperature signal that's like, looks something like that, doesn't matter. For this demonstration, I'm just putting in a 10 hertz signal just to show what happens. But this aliasing effect comes up no matter what you're doing. So anyway, so there's what reality looks like. It's a 10 hertz signal. If I sample at 100 hertz, the thing to notice here is it doesn't look perfectly like this one over here. But if you were to measure the frequencies here, it's pretty good. The amplitude's pretty close. So it's a pretty good representation. You got the right shape and you've got the right frequency in there. And so this was at 10 hertz, was our reality. And this is sampling at 100 hertz. Now, if we sampled, let's say at, just because we could, let's sample at 12 hertz. This is 12 hertz, got cut off at the bottom. You can see that this in no way looks like our reality here. Our frequency's not right, our amplitude's not right, but really what's happening is we get to the right point and we take a measurement. And these dotted lines indicate we don't actually know what happens in between them. Our data comes in and it looks like just these points, right? Yeah, same up here and for all these, and we're having to extrapolate in between them to figure out what our data looks like. And so we can see that this does not represent this 10 hertz signal at all. It's even worse if we do something like, say, sample at 2 hertz. Now we've got something that doesn't even look close to what our reality is. But if we weren't paying attention, we'd say, oh look, we got this nice sine wave. I knew I was getting a sine wave, and getting a sine wave out, good enough. But you can see that the frequency doesn't match up at all. So aliasing overall is basically a way that you can accidentally misrepresent a signal by not sampling fast enough. And so how we combat that is this thing called the Nyquist theorem. And we got some advanced math here, right? Basically you want to sample at least twice the rate of your highest frequency to accurately represent something. So, and that's just to get the frequency right. If you want the shape to look right and you want it to look like a good graph, the standard advice is at least 5 times, but more like 10 times the sampling rate will help with that. So, but at least 2 times to get the frequency correct. And so that's basically aliasing in a nutshell. Let's see what's next. Okay, so some other things that come up. I have this single versus differential ended. So if I have some sensor out here, way out here, there's 2 ways we can handle this. we can either, suppose this is our data acquisition, and starting now you're going to start to see me write DAQ for data acquisition. It's going to become more common. If this was an in-person class, I'd be handing you a data acquisition unit for you to use in your labs, but I wasn't going to pass them out with everybody. So, but maybe this data acquisition unit has 4 channels. A single-ended connection would mean we could put 4 sensors out there. And what that does is one of them is tied to the channel, and then we assume there's a ground. And that's basically the other end of each of these sensors. We'll talk about grounding, I think, in maybe next week. But the bottom line is, that's one configuration. That's single-ended SE. Differential-ended. Say we got the same 4-channel device. But what happens here is I use 2 channels for each sensor. And there's advantages and disadvantages to both. I mean, for one thing, it's like, oh, I can take 4 measurements here and I can only take 2 here. The real problem is for a lot of things we do in lab, we can get away with using a single-ended connection. Some sensors prefer a differential-ended connection. And the idea with this is, we'll talk about antennas next week as well, but the longer wire I have, the better of an antenna it acts as. And so if you're building an antenna, that's great, but the reality is, if I'm trying to measure pressure over here, I don't want this piece of wire absorbing a bunch of other signals, because that's just adding to my noise. And so instead of getting maybe, you know, some nice, maybe pressure's increasing and I got something like that, rather than get that, if I have this thing acting as an antenna, maybe it looks like that. And so I don't like all that extra noise that may be in there. So when you use the single-ended connection, or if you have a common ground, and what I mean by that is if all these sensors basically are sharing the same ground, and so that's kind of what we've drawn here. You also can only get away with single-ended connections if you have big changes between things. So if this is going between 0 volt and 1 volt, you know, if your step change, I would say if your step change is half a volt or so, you can get away with single-ended connections. Also, if your connections are short. So if you've got shorter wires, you can get away with it. For example, you wouldn't want to put a bunch of strain gauges on a bridge, say. Suppose you got some bridge that's a mile long. You wouldn't want to put a bunch of strain gauges on there and then connect them with a single-ended mode connection, because you just pick up so much noise, and you'd be better off using differential mode. And the differential mode, the deal with it is, yeah, these are still acting like antennas, but if this is the positive side and this is the negative side, and these wires are the same length, they're absorbing similar noise. And so you can actually subtract, so the noise you're picking up, the other electrical interference and such, are partially getting canceled out because you've got 2 wires and one of them's positive and one of them's negative. So that same noise is getting canceled out. There's some other techniques, and we'll talk about that a little more next week. But so anytime you need, anytime you have long connections, you need to run long wires to a sensor. Anytime you have little tiny step changes, where like these big step changes, if you have a noise signal on it, maybe it doesn't matter. So that's why you can get away with a single-ended. But if you have some small step change, like you might get off of a thermocouple for measuring temperature, you've got to use the differential mode. And of course, the differential mode, you only get to take 2 measurements versus 4 in this case. And that's just one of the disadvantages, I'll say. So, with that, and I go through all this here. I kind of point out a couple sensors, thermocouple, strain gauges that just really work out well for differential mode. So putting this all together, we got a lot of things to think about when we design an instrumentation system. We got to think about things like, what am I actually measuring? And what I mean by that is, you may think you're measuring temperature, You know, it's like, oh, I'm measuring temperature, but I'm using a thermocouple to do it. So what I'm really measuring is a voltage. Or, oh, I think I'm measuring pressure, but I'm using a capacitive pressure gauge, so I'm actually measuring capacitance. And this comes up sometimes when you start to have to troubleshoot. Like, you think you're measuring temperature, but what are you actually measuring? And you guys know this because, like, on the other end, on the control end, it's the same thing. When you turn the volume knob on your stereo to turn up the music, you think like, oh, I've turned it to 11, but really that number doesn't mean anything. What you've actually done is probably tuned an inductor, so you've changed the inductance, which ends up changing the output actually probably output current to a speaker. And I already used I for inductance. I should have used H. Anyway, you get the idea. This doesn't look anything like this, but this is how we control it. The same thing's happening here. Our temperature sensor is really measuring voltage or resistance or whatever it's measuring. So we'll have to look at that. And when we're troubleshooting, that'll come up. We have to know a little bit about how our sensor works. And I've said in the past, this instrumentation class, I don't go into a lot of how different sensors work because new sensors are being developed all the time. You just got to get into the habit of learning how your specific sensor is going to work. Rather than me covering hundreds and thousands of types of sensors, you're just going to have to figure that part out as you get a new one, versus trying to like memorize which ones I know about. So you need to think about how many bits are required. You know, what resolution do I need to have and why? How many bits do I need? We need to worry about how fast we should sample, our resolution in the T direction. So how fast in this direction and how fast in this direction. I need to think about, do I want single or differential mode? Also things like, how do I store the data? How much record keeping do I need to worry about? What kind of statistics do I need to perform? Is any of this going into a control loop? How do I manage all this data I'm collecting? And so on and so on. So these are just a kind of a big picture of all the things that go into designing an entire instrumentation system. So stole everything as usual. And that's what I have for you.